All right, so to transition into the plenary, I want to highlight a new initiative that folks have spearheaded, which is the supporting today's plenary. So the Dale Lundgren and Virgil Marple Plenary Lecture. This is the inaugural Lundgren-Marple Lecture, and it's kind of celebrating the collaboration and friendship of Dale Lundgren and Virgil Marple, and the huge advances in aerosol instrumentation that came out of this partnership. And it's a fund that is sponsoring this and has just been set up, so we just sort of reached the target to start out this fund. And I want to highlight that if you'd like to contribute to this fund, there's a link up here on the website to support that. So to introduce the inaugural Lundgren-Marple Lecture, I'm going to ask Hans Moosmiller from Desert Research Institute to come up. And I want to say, unfortunately, the speaker today had a family issue arise and wasn't able to be here in person, so he'll be here. But fortunately, he's able to present via Zoom. So, Hans?
Thanks, Andy. It's an absolute pleasure to be here and introduce Wanderley Martens, who has been in the aerosol community for quite a while. Wanderley is originally from Brazil and came to the US to work at Goddard Space Flight Center, both on the MODIS instrument and was on the science team of the Glory mission. And since then, he's moved next door to the University of Maryland, Baltimore County, UMBC, where he's a professor of physics. He is also the director of the Earth and Space Institute, leads his lab for aerosol clouds and optics. And I first met Wanderley in 2011. I was visiting Loreen Riemer, the chief scientist of MODIS at Goddard, and Loreen says, Hans, you gotta take an extra day and meet Wanderley at UMBC. You're both interested in instrument development. That'd be a great combination. She didn't tell me how impressed and humbled I would be by seeing Wanderley's work. At that time, he was developing an imaging polarized nephelometer, multi-wavelengths, really transformative progress, where the different angles of scattering are imaged on a CCD array instead of measuring one at a time and having to keep a stable aerosol. Real progress, and normally when we develop instruments, we hit the valley of death and things kind of don't move forward, but Wanderley went through that. He proved it, the instrument in the lab, then participate in NASA laboratory and field studies, including deploying it on an airplane, doing very successful measurements of the scattering matrix. And so I was just totally impressed by Wanderley, but then he told me he's going to develop a satellite instrument. And I thought, he's gone mad. No, completely, utterly mad, because I just couldn't imagine how somebody would keep up with all these design reviews and paperwork and hoops. But Wanderley just plowed ahead. He first developed AirHarp for suborbital measurements and proved the concept of his imaging polarimeter on an airplane. Then NASA had this CubeSat program, or still has, to involve more university scientists in development of satellite instruments, and he had, I believe, a couple of CubeSats. And now he's hit major times, and next year NASA is planning to launch the PACE mission, phytoplankton, aerosols, clouds, and aquatic ecosystems. And there are three major instruments on there, including Wanderley's HARP-2 instrument. So hopefully the launch will go well, and we'll get data from that, both on the atmosphere and aerosols and the ocean. Now, in conclusion, Wanderley is really one of the smartest, friendliest, and most low-key scientists I've ever met. And so I hope you will enjoy his lecture, and I'm sure you will. And please join me in welcoming Wanderley and seeing his talk. Wanderley?
Yeah. Thank you very much, Hans. Thank you very much for the kind introduction. And and it's a great pleasure, great honor to be here for this lecture. And I am really, really sorry for not being there in person. So I had a very strong family emergency and there was no way I could travel. I really wanted to be there in person for this lecture and for this exciting meeting. But anyway, thank you so much for the invitation. And thank you very much for being here today. And it's a great honor to be here, especially this lecture in honor of Dale Lundgren. So, and I wanted to find at least one connection with part of the work that I'm doing with NASA. So I went back to this report from NASA and this conference that Dale participated and was bringing in-situ measurements to the NASA community, which is very connected to what I'm going to be talking about here today. So it's really a great honor to have this introductory lecture to this series. So what I'm really going to be talking about is the connection between the measurements or between the particle properties and the optical properties in general, the microphysical properties and the optical properties. So most of my work is focused on measurements of particle properties based on optical measurements, and in particular about angular measurements, like looking at phase functions or phase matrices from different aerosol particles, like you see, for instance, the case for dust, where we have a strong forward scattering peak. So this is like phase function as a function of scattering angle. And you see, as an example, the difference between dust phase function, or one case of dust phase function that we had, and one case of smoke, both with combination of small and large particles. And there are significant differences in the angular distribution of the phase function between these two aerosols. And that's what we use. So what we do, so my main work is to measure different points or to measure this phase function at different angles, and then use that information to invert optical properties of the aerosols or microphysical properties of the aerosols. So for instance, what you see here are two inverted size distributions that are inverted based on the measurement of these two phase functions here. So you see from the phase function for smoke, the size distribution that we got with mostly fine mode, an electron microscopy picture of those particles collected in a filter, in a nuclear pore filter. So the white are the particles. So you see small, mostly spherical particles in this case, corresponding to the size distribution I have here and to the black phase function. And then we see for dust, so the red size distribution with mostly coarse particles, and you see here an electron microscopy picture showing some of those particles, so non-spherical, larger particles. So you see the 1 micron bar here. So again, most of what I'm going to be talking about today is about these angular measurements, either just intensity measurements that I'm showing here, or more completely polarization measurements. So basically we're interested in the incident radiation in the particle and the state of the incident light. So in this case, I have here the Stokes parameters I, Q, U, and V representing the incoming light. And then as the light interacts with the particle, we look at the scattered light at different angles as a function of angle. And we look again at the Stokes parameters of the scattered light. So I, Q, U, and V, depending on the measurement. So in some cases, we're measuring just I. In other cases, we measure the full Stokes vector, so the 4 parameters. And basically, what you're interested is in the scattering matrix of the particle. So what are the parameters that define this interaction between the incident light interacting with the particle and then producing the scattered light? And we measure the scattered light, as I said before, and we're going to use those measurements as a function of angle to invert the microphysical properties. And we go beyond just intensity. So here I'm showing again the plots for intensity, for smoke, and for dust. But we add the other Stokes parameters, and part of the motivation for that is that the other Stokes parameters contain additional information that would be important to characterize the particles. So for instance, this is an example showing how the polarized phase function can vary as a function of refractive index. So there is information on the refractive index in the polarization measurements. So we are going to use not only the intensity as a function of angle, but some of the other Stokes parameters, like for instance, P12, polarized reflectance in this case, to characterize refractive indices, shape of the particles, and other pieces of information that would be hard to achieve by just measuring intensity. So what I'm going to be discussing here are the measurements of, again, the angular distribution of the scattering of particles and how that angular distribution can be used to invert the particle properties. But really my goal here is to make a connection between those kind of measurements, those kind of angular measurements that we can do either in situ, or we can do from satellite, or we can do from the ground. For instance, in this case, most of you may be aware of AeroNet, which is a angular measurement of phase function of aerosols that we do from the ground, but over the total column. So this will be measuring the total column of aerosol from the ground, from the surface, all the way to the top of the atmosphere. And we get the angular measurement by initially pointing at the sun, and then you can get the direct measurement of optical thickness or optical depth by looking directly at the sun. And then by scanning the instrument at different geometries, so for instance, making a circle around the solar zenith angle, so you get different angular measurements or different scattering angle as a function of the position where you do the measurement. So if you do very close to the sun, you have very strong forward scattering. If you do on the other direction, opposite to the sun, you can get all the way to some angles in back scattering. And then by doing measurements around this circle, I get measurements of different scattering angle as the instrument is scanning. You can also do other kind of measurements, like principal plane measurements, where you point at the sun and you basically scan in that principal plane. And then from the measurements in the principal plane, you get, again, different scattering angle measurements. Again, this is a way to measure as a function of angle, but the total atmospheric column. And you see later, one of my goals here is to make connections between the total atmospheric column and measurements, in situ measurements at the nose level, in situ measurements where people breathe. So that's the direction that I'm going. So these are measurements from the ground with an instrument like AeroNet, and there are other instruments that make these measurements as a function of angle from the ground. I can also do something similar from aircraft or even from space, where here now I have, for instance, a wide field of view instrument in the long track direction or in the direction of flight, right? So the aircraft or satellites flying in this direction, and if I have a very wide field of view in that direction, by measuring the different lines of sight, so the different instantaneous field of view, I can also get different scattering angles, right? So in this case, if the sun is over here, I can get a backscattering measurement. So I can get a measurement as a function of scattering in the backscattering direction. And if the aircraft keeps moving, if I look at the same location on the ground, now I'm looking backwards from my instrument, from my wide field of view instrument, but that produces now a forward scattering, right? So if you look now at the sun in this position, and you look at the scattering angle, now I have a scattering angle less than 90 degrees. So 90 degrees would be here, and I have now less than 90 degrees, so therefore this is a forward scattering measurement. So there is a limitation on how far you can go in the forward direction, how far you can go in the backward direction, but you can cover a pretty good range of those measurements. And that's the way I will show you later how we are doing these angular measurements, either from aircraft or from space, is by having this very wide field of view instrument that's measuring in the along track direction in a way that by looking at different fields of view, you can get different scattering angle measurements. So this is from remote sensing perspective, so either from the ground or from aircraft or from space. We can also do similar measurements in situ, right? And that's what Hans was referring to initially, what we call the polarized imaging nephelometer instrument. So it's also a very wide field of view imager, and we have a laser beam that if the laser beam is moving in this direction that I'm representing here, you take the wide field of view measurements, and if you look at scattering by particles on the way, on the trajectory of the beam, if you get a scattering action, you are looking at forward scattering at a given scattering angle. You look at another position of the particle inside the chamber, I have now a different scattering angle all the way to 90 degrees scattering angle. So I can, by measuring the particles in different positions in the beam, get different measurements of intensity scattered as a function of scattering angle, all the way from small angle, and we did measurements from 3 degrees forward scattering, all the way, in this case, to 90 degrees here in one side, and we have the beam, the laser beam reflected. So I have the laser beam going in this direction initially, it hits a rectal reflector, gets reflected back. So in one direction of the beam, I get back scattering measurements. Now you can see that the particle is here, laser beam is moving from left to right. Laser beam hits the particle, it scatters back towards my ear, and then I get a back scattering measurement. If I get the other portion of the beam that now is moving in this direction, I can measure in that branch the forward scattering direction. So this is one way to do the geometry, and the only reason to fold the beam the way I have it here is to reduce the length of the instrument, so to have a smaller instrument. But we also have done the same with a single laser beam and the imager at 90 degrees with a very wide field of view, measuring all the way from forward scattering to back scattering in a single beam. But the point is, if you image in the different angles, you get measurements of intensity at different scattering angles. And we have done those measurements for purely intensity, like phase function. We also have done by measuring Stokes parameters, by adding a polarimeter to the system. You can also polarize the laser beam, as the laser beam is incident. I'm going to take a step back here and introduce the initiative that you are doing in terms of doing these in situ measurements. So this is an initiative that we started at the university, and then we, from there, incubated 2 companies to keep these measurements and to spread this type of measurements beyond what we could do at the university. And this is the initiative of 2 companies, one in Europe. So this is the GRASP SaaS company in Europe that was a spin-off of the University of Lille, started by Oleg Dubovic in France. And then our initiative, AirPhoton, that's a spin-off at UMBC, so it's incubated by UMBC, where we focus on the development of instrumentation. So GRASP is focused on the development of the software for inversion, for producing results, this kind of measurements, either from space, from aircraft, or from ground. And AirPhoton is focused on the instrument development to do these measurements, again, either in situ, total column, or from aircraft and from space. So today we are merged in one company promoting these kind of measurements. And we moved to measurements beyond the PINF, beyond the polarized imaging nephelometer, to multi-angle measurements with discrete sensors or discrete light sources around the volume that we make the measurement. And the reason we moved in this direction is, one, to miniaturize the instrument, to have a simpler instrument that can be easily placed in an aircraft or be spread in many locations, and also an instrument that does the measurement in a smaller volume. So for the laser nephelometer that you saw, we needed a large volume in order to get all the angles that I need for my imager. And if I'm doing in-situ measurement and I have a large volume in a large chamber, it takes a while to replace the air and the aerosol inside the chamber, so my response time is relatively small. In this case, I can have a response time in seconds, and I can have a relatively small instrument. So this case, for instance, is 3 inches chamber, and most of the measurements are done in the center of the chamber. And with that, we can do measurements of intensity as a function of angle, as you see here. So we do that in 3 wavelengths in our first instruments. And we can also do polarized measurements by measuring some of the Stokes parameters that in this case we convert to polarized reflectance, and we have the polarization measurements. So from the intensity measurements as a function of angle and from the polarization measurements as a function of angle, again, we can get size distribution, we can get refractive indices, we can get sphericity of the particles or parameters related to the sphericity of the particles, and etc. And our main goal with this is really to do measurements, in-situ measurements, similar to the measurements that you are doing from the satellite. What I mean by that are multi-angle, multi-wavelength, polarized measurements that we do total column from the satellite, total column from a aeronet-like instrument at the ground level, and in-situ measurements with instruments like either the PINF or these multi-angle instruments that I'm showing here. One example of this multi-angle instrument is what we call the IMAP instrument. So the IMAP is measuring scattering and polarization at 3 wavelengths, in this particular case at 8 different angles, like I showed you before, but also with a aerodynamic cutoff, aerodynamic cyclone for the cutoff size at different sizes, different size ranges, to make the connection between the aerosol that we breathe and the optical measurements that we are doing, again, from satellite, from ground-based total column, or from the in-situ instrument. So the idea is really to run these instruments all together and get a full picture of the measurement. So as I was saying, right, so we want to connect the total column from the satellite with total column from aeronet-like instrument, but also connect that with the nose level measurements, both aerodynamics, so that we can connect with what we breathe. And I know you're all very familiar with that much more than I am. And but we want to make the connection between the aerodynamic measurements and the optical measurements, because all the satellite measurements are optical measurements, right? So all the aerosol measurements from satellite are inversions that we do from the angular scattering, multi-wavelength and polarization scattering measurements that we do from space at different angles. So how do I make the connection between those measurements from space, measurements now at the ground level, both using the same technique, right? So multi-angle scattering, polarization, multi-wavelength measurements. How do I connect that with the aerosol that we breathe? And to me, I know other people have done this before, but to me, this connection needs to be strengthened, right? So I need now instruments or different types of instruments that are measuring similar multi-angle polarization, multi-wavelength scattering, but in situ, at the nose level, that is also connected with the aerodynamic measurements. So really our goal is to make the connection between the aerodynamics and the optical measurements inside the instrument. And we have done that in different ways. So here I was showing you some, this is simulated data, but we also have measurements now. So these are all new instruments but they are being spread. We have a few of these instruments in Europe and some in the US at the moment. And this is an example of actual measurements of I, Q, and U, as I said before, some of the Stokes parameters that we use, for instance, to get degree of linear polarization. So these are measurements as a function of angle, and you see how varied it is, right? So in terms of intensity as a function of angle for this particular type of aerosol, in terms of Q, right, or Q over I, right, Q over intensity, you see how that varies, and also U as a function of intensity. So the red dots are actual measurements done. In this case, I'm showing you examples from the satellite, from the HARP satellite, and I'll talk more about that in a moment. And in black is actually the GRASP retrieval. So I mentioned before that GRASP was, that software is also a company, but it's the software that does the inversion of the particle properties, inversion of the size distribution of the aerosols, an inversion of refractive indices, the sphericity of the particle, and the amount of aerosol. So that inversion is based on these fits. So the black line is a fit done by the GRASP algorithm that then inverts on that a lot of details about aerosol microphysics. But I still want to make the connection with the aerodynamics. And the way we are doing the connection with aerodynamics, as I said before, by using cyclones with the different instruments. So being a multi-angular instrument that I was discussing before, or even in this case, a integrating nephelometer. So if you take the integrating nephelometer and I have my cyclone on top, in this case, what we are doing is we're varying the flow rate in the cyclone. I have my cyclone for, PM 2.5 at 5 liters per minute. And here I have two different measurements of the integrated scattering, one with the cyclone running for PM 2.5, and the other one for the cyclone running for PM1. And you see the difference in total scattering measured in those two cases. So PM1 here, PM 2.5, and we can go all the way from PM1 to PM10 by varying the speed, and we have a flow control in the instrument that can automatically vary the speed any way you want, right? So you can either, in this case, I'm taking two cases, two flow rates, just to show an example of the stability of the two flow rates as we vary, but this could be a sinusoidal variation of the flow rate and sinusoidal variation of the cutoff size of the cyclone, or it can take any shape you program for that, all the way from PM1 to PM10. And what we gain by that is that now, even with an integrating nephelometer, so here I have an integrating nephelometer with 3 wavelengths, forward scattering and back scattering independent measurement. And there are several limitations in terms of those optical measurements. But if I add now a cyclone that I can vary the cutoff size of the cyclone and I take that into account, I can now use softwares like GRASP, the GRASP algorithm, to now do a full inversion, even from the measurement of an integrating nephelometer, and from that measure or get estimates of the size distribution, of a full size distribution. Just because you have enough parameters from the back scattering measurement, the forward scattering measurements, the 3 wavelengths that we're measuring here, plus the different cutoffs in aerodynamic size. Like for instance, if I do PM1, PM2.5, PM4, and PM10, if I add all these pieces of information together, you now have enough information that you can retrieve size distribution and the other properties, even if you start with a limited measurement, like an integrating nephelometer. Now, if you go to more complete measurements, like I mentioned before, multi-angle measurements and polarization measurements, then you have even more information. So if you have now the aerodynamic size and you have information coming from fit, these polarization parameters as a function of angle, you now can have a lot more information, right? And you can get much more accurate. So these are simulations, but it's the best way I can show you what we are doing or the direction we are going. So here you have the reference size distribution in gray, and the other colors are the retrieved size distributions if I use my cyclone at PM4, PM5, PM6 in this case, just to show some variation of the inversion with two cases of aerosols. And these are aerosols that were measured at Kanpur, so we use that as a reference for the simulations, Kanpur, India, or aerosols at NASA Goddard, because I had in those cases larger coarse mold here. So this is now, again, combining the aerodynamic measurements with the optical measurements in order to get better representation of my optical measurements to represent the aerosol that we breathe. So our real goal here is, again, to make the connection between the aerosol that we breathe at the nose level and in-situ measurements, in-situ optical measurements, and total column optical measurements, either from satellite or from ground-based. So I do want to make the satellite connection. And because of that, I'll take now a step back and talk a little bit about satellites so that they can bring this out together at the end. And in particular, I'm going to be focusing at what I consider the next generation of passive aerosol measurements from space. Like, for instance, the next NASA missions measuring aerosols are measuring multi-angle and polarization. Also from Europe. So there are several missions coming from Europe measuring multi-angle and polarization because of the richness of information that you get from these measurements in terms of aerosols. So, I started my work with remote sensing with the MODIS group at NASA, which is basically one angle intensity measurement with broad spectral range from, the blue all the way to 2.1 micron. It goes to VIRS, that does similar kind of measurements. In parallel with MODIS, we had the MISR sensor by JPL that was doing narrower spectral range, only up to 870 nanometer, but multi-angle measurements. And that was the first time, at least, I saw the power of the multi-angle measurements. And then we are moving from that to multi-angle imaging polarimeters so that we can get multi-angle measurements and polarization altogether. And here, I'm actually borrowing this chart from Oleg Dubovik with some modifications that I did in the chart, but basically showing the range, or more or less the range of angular measurements that we do with the different measurements. So if you do, for instance, measurements with aeronet at the ground, you can measure as a function of scattering angle, but there are some limitations. There are some limitations based on the solar angle, for instance. So what's the solar zenith angle during the time that you do the measurement? And you can never go all the way to full backscattering, right? So all the way to 180 degrees. But there is a range that can be relatively large, depending on the time of the day that you're doing the measurements. But those are the measurements you do with aeronet, but as a function of angle. And then you have measurements like integrating nephelometer, where you're limited, right? So you get the integrated measurement. And in our case, we measure from 7 degrees to 90 degrees. So we measure forward scattering. It's one number here, right? So integrated. And we measure from 90 to 170. So another number. So we measure one number for forward scattering, one number for back scattering. We also have the polar nephelometers that I should have put here. We resolve as a function of angle, right? We can have very fine angular measurements from the polar nephelometers, or the case I showed you also where we're measuring only 8 angles. But we can cover a very broad range. So all the way from, let's say, 5 degrees, or we have done even 3 degrees, all the way to 175 or 177 degrees in the backscattering direction. And then you go to LIDAR, where you're focused at 180, right? So it's fully backscattering measurement. At the moment, my knowledge, the only fully backscattering measurement that we have on the LIDAR side. Or you go to remote sensors like MODIS that I said before. So it's one angle, right? It's one angle at a time, but because of variation in the cross-track swath or variation of solar angle, that one angle that you measure can vary substantially, all the way to close to 180. Exaggerated here. We don't get all the way to 180, but you can get close to 180. But we start at something like 50 degrees or so, 60 degrees or so. So there is limited range, a little bit on the forward direction, but mostly in the backscattering direction, but one angle at a time. So each retrieval is done at a single angle. And then you move to the multi-angle measurements that have similar range as we have for MODIS, but with the advantage that we can resolve angularly. So we do the measurement at multiple different angles at the same time. And that's the advantage, right? So my retrieval is going to take the whole angular information and the polarization information in addition to the multispectral information. Just to give a perspective of where we are today, because this field evolved quickly. So today we actually have had several polarimeters already flying in space in the past. So starting with the PODER instrument from France, all the way from 1996. So they had the first data set measuring multi-angle and polarization with very, very successful results. All the way in our case, we had the HARP CubeSat from all the way to April 2022. So this should be 2020. So we had data from 2020 to 2022 from the HARP CubeSat, and I'll talk more about that. And some polarimeters that we have in space until today, several of them from China, one from Japan, and we have actually our own commercial polarimeter flying in space right now, so GapMap 0. So all the ones I put stars, so those are the ones that I'm involved directly, and I'll talk at least a little bit about them in this presentation. And here I put the stars in green because they're repeated, right? They're the same as here. So we have 5 polarimeters that have been involved in space. But in the near future, we have some very exciting instruments coming. Some of them pretty soon. We have the HARP-2 instrument that I'll talk more in a moment. So that's going to be launched in early 2024 in the PACE spacecraft, so by NASA. So that one will give us global measurements in 2 days. We have SPEX-1 from the Netherlands that's going to be flying together in the same satellite. We will have GapMap-1, so it's a follow-up to our demonstration, the GapMap 0, launching early 2025. We have another polarimeter from Europe, so the MAP and CO2 measurements together in 2026. And then we have 3MI, also for global measurements, 2026. Have Maya from JPL, 2026, very focused on air pollution and health effects. And we have AOS from NASA, very advanced measurements, but for 2028. So there is a lot coming in terms of the future of these measurements. And I just want to illustrate here briefly some measurements. So these are measurements done by PODER. So these are pioneering measurements inverted with the GRASP algorithm. So showing measurements of optical thickness, angstrom exponents, single scattering albedo, scale height. There are also measurements of sphericity and refractive indices that you can get from these techniques. But I want to briefly introduce the HARP CubeSat satellite. And Hans, please correct me on time. Like, please give me a warning when my time is ending. So we had launched, as I mentioned before, the HARP CubeSat satellite. So CubeSat is a very small satellite. It's the size of the loaf of bread, basically, this particular one, right? So this is a 3U satellite. And this sensor was designed to measure polarization, 3 angles of linear polarization. So we measure intensity at 0, 45, and 90 degrees. We measure that at different wavelengths. So there's a filter that separates the 4 different wavelengths from 440 nanometer to 870 nanometer. And then by selecting individual filters, this is a very wide field of view sensor, right? It's a very wide field of view image in the long track direction. If I take just the first line, I'm looking at an angle, actually, first line. If I take just the first line here, I'm looking at a forward view. So by reproducing this image multiple times as the satellite's flying, I get a forward view image just from that individual line, from that individual filter. I can do that for my 4 filters, so I get my multi-wavelength image at that particular viewing angle. If I take a line from major, I have now my major image. If I take a line from the back of my sensor, now I have the backward direction. And the combination of these viewings and the solar angle gives me the multi-angle measurement that we are interested in. And then the combination between these 3 different images that you're taking simultaneously, you can see that the images have slightly different features. For instance, here, right? So by combining these 3 images, I get my 3 Stokes parameters and my polarized measurement. So basically, as I was mentioning before, so it's multi-angle measurement, because as the satellite's flying, I look at the same location on the ground from different angles, different positions of the satellite, but same location on the ground. Then I get multiple wavelengths, and we get the different wavelengths, 4 wavelengths in the case of the satellite. So HARP had up to 60 different viewing angles, and that's what you see here. So those are measurements at different viewing angles. And up to 20 viewing angles for other 3 wavelengths. So 60 viewing angles for 670 nanometers. This is mostly for cloud measurements, and 20 viewing angles at other wavelengths. And combining both, we can get very good aerosol measurements from space. So HARP was a simple demonstration, right? In preparation for the future missions, in preparation for HARP-2 that's going to fly on space, and in preparation for future missions like AOS. So it's a very limited instrument, very limited satellite, very capable instrument, but very limited satellite because of the very small size. So during 2 years in orbit, those are all the images we collected, but it is a lot of data because of the different wavelengths and all the scattering angles that we got. So again, the goal was to do a demonstration. So these are intensity measurements, then polarization measurements. I really don't have time to go in detail on the polarization measurements, but you see how the features change, right? So if I'm looking at polarization, there are features that show up in the image, either for clouds or for aerosols that I wouldn't see in an intensity measurement. And that's what we use to add information to the retrievals. So this is just zooming just to give you some better perspective. So really the polarization measurements give a lot of additional information that I wouldn't have with just intensity measurements. So HARP was a very successful demonstration. We were able to move to these other efforts like HARP-2. Just by curiosity, I'm showing you here how these guys get to space, right? Or one of the ways that they get to space. So you actually launch them in a large rocket. The large rocket has a spacecraft like this one that gets deployed from the rocket, goes all the way to the space station. At the space station, so these CubeSats, the satellites are handled by, the spacecraft docks to the space station. An astronaut grabs the CubeSats, grabs the instrument inside the space station and put in these, I call them torpedo launchers, but these deployers, right? So these systems that will now launch the CubeSats to space, like what you see here. So the space station basically shoots them out like little torpedoes almost. And then they're on their own. So they're flying on their own and collecting data after that. So these are some examples of multi-angle images that we got from HARP. And you can see here, for instance, a case of dust leaving from Africa. For different angles, these images were, just a few minutes apart, right, from each other. And from the different angles, I'm measuring scattering as a function of angle. So you can see how the color here changes as a function of scattering angle. So that's what gives me the quantitative measurements, quantitative information that I have from the satellite. And here's just an example again showing the multi-angle from a given location from HARP, multi-angle from dust leaving Africa, and a couple of days later, or several days later in this case, dust that left Africa and are now in the Americas, right? So we have quantitative measurements from events like this, And with the GRASP algorithm, we can invert from the multi-angle measurement to amount of aerosols and size distribution and the other properties. So you get very detailed information, similar to the ones I said that you get in situ, but now measurements from space. And again, my goal is always to connect them both together, right? So to bring them together with similar technique, similar multi-angle polarization optical measurements, either total column or in situ, and then on the in situ side, connect that with the aerodynamic measurements. So this is just an example of smoke from Oregon and California. In this case, an example of the retrieval. We have done some validation. I'm not going to go in a lot of details of that, but these are, some cases where we showed validation with Aeronet and the measurements from the satellite. So I'm almost running out of time here, but I want to introduce a little bit of future measurements like HARP2. And just to give you a perspective, so this was the HARP CubeSat satellite. This is the HARP2 instrument that you see here. So HARP2 instrument is a little bit bigger than the CubeSat, but it's mounted to a much larger spacecraft. And now, because of a much larger spacecraft, we have a lot more resources, right? And then when HARP2 does its measurements, we're going to be able to do measurements basically covering the globe in 2 days. So here you have an idea of the swath of the HARP2 instrument, how it is a simulation of how it will be in space, and showing that in 2 days we can basically cover the whole globe with multi-angle measurements and polarization measurements that will allow us to do these measurements in a lot of detail. So HARP2 will be launched on pace in beginning of 2024, January, February 2024. So it's very exciting. It's fully integrated. The spacecraft has been fully tested, fully calibrated. And again, one more time, just to emphasize my point here, there is a lot of synergy between the measurements that we do from space, measurements that we do at the ground, total column, and the nose level measurements that I was mentioning before. And our goal is to bring all together to the same kind of inversions so that we can perform these measurements in a synergistic way. Just briefly, so I mentioned that we also have the a commercial satellite in space right now. So that's the GapMap satellite, and our goal with the GapMap satellite is to actually have a constellation of satellites doing the same type of measurements. So we have GapMap 0 in space right now, starting to provide some data. GapMap 1 will launch in 2025, and we're still working on funding for the other satellites after that. But we do have a successful demonstration running in space right now. So that's the GapMap 0 polarimeter, producing data already very similar to HARP that I showed before in multi-angle polarization and 4 wavelengths. It's a different instrument than HARP, but it's a very, very similar instrument to HARP. And I want to end here. I mean, there's a lot more that you could talk about each one of these measurements, but I want to leave time for you to ask questions if there is any left. But basically, what I want to say here is a very simple message, right? So our goal, or my goal, has been to add these nose level measurements for air quality and health applications, but in combination with the total column measurements that we do either from the ground or from satellites. So I want to bring these measurements together. And I know many people have done that in different ways, but we are trying to add the same kind of measurements. I want to make sure that the optical measurements that we do at the ground level, that we do at the nose level, are the same measurements that we're doing from space. They're the same technique. They're multi-angle polarization at similar wavelengths. So that the inversion technique that I use for the satellite is the same inversion technique that I use for the nose level measurements. And the reason I want to do that is because at the nose level measurements, I can also do the aerodynamic cutoff, right? So I can do measurements on the aerodynamic side and make this connection between aerodynamics and optical inversion. So how these two quantities relate to each other. And then since I'm doing the same optical measurements at the ground that I'm doing for total column and for the satellite, I hope to do a better synergy between the aerodynamic measurements at the ground and the satellite measurements. Of course, satellite measurements are total column and they do not represent exactly what you see at the surface, but we're trying to bring that gap closer and make these measurements together, aerodynamics and the optical measurement. HarpCubeSat had a very successful campaign, ended its life on 2022, flew successfully for 2 years. Thanks to that, we have HARP2 on pace that's going to come in spring 2024, provide the same kind of data from space. We have GapMap flying right now. Hopefully we'll have a constellation of the satellites, because the more measurements we can bring from space, the more information we have on daily cycle and the other pieces. And we are working on this extended HARP system for future measurements, which will be from UV all the way to short-wave infrared, again, to add more information on the retrievals. So I think in terms of multi-angle polarization measurements, the future is very bright, right? So it's coming, it's happening right now. We have these measurements. What we are trying to do now is to add more and more of these instruments at the nose level, doing similar measurements, so that we can have very synergistic retrievals for both. So thank you very much.
Well, Wanderlei, thank you for this excellent and informative talk. And we still have a little bit of time left for discussion. So are there any questions or many questions from the audience about Wanderlei's work? Yes, please.
Jose Moran from University of Minnesota. Obrigado for this nice presentation. My question is, all along your presentation, you mentioned some inversion that is needed. So I wanted to ask you why we need to do this inversion and what are the key assumptions of this?
Let me see if I have one example here. Yeah, unfortunately, I did not add in this presentation more discussion on the inversion. But the reason you need to do the inversion is, let me go back to this, is that this is what I'm measuring. So these are the direct measurements that we are doing, right? So measuring intensity as a function of angle and gives beautiful information about the optical properties about that particle, but gives me very little direct information on the microphysics of these particles. And same thing for the other polarization parameters, right? So these are excellent information in terms of the optical properties or how the particles interacted with radiation. But one of the pieces of information that we are all very interested in is what are the microphysical properties of these particles? So what's the size of the aerosol, for instance? So if you want to make any connection with aerodynamics, I need to know more information about the size, right? The size of the particles. And I need to get somehow that information. Like for instance, if I want to get my size distribution, right? So how do I get that? So starting from the optical measurements, I have to now somehow determine the size of the particles that generated this scattering pattern. Turns out that you have enough pieces of information here to actually retrieve a very detailed size distribution, like what you see here. These are inverted size distributions, and this inversion was done based on those optical measurements that I showed before. Intensity as a function of angle, polarization as a function of angle. And what you're trying to achieve is what was the size distribution that generated that scattering pattern. What's the size distribution that generated this scattering pattern that I'm showing here? I'm asking that question mathematically. And there are many assumptions that you have to do in order to do this kind of inversion. And the good news is that the GRASP algorithm, that's the one that we're using to do this inversion, has been very well studied over many, many, many years. in terms of minimizing the assumptions or determining what are the best assumptions that you can do for this kind of getting a reliable retrieval on the other side. But some of the assumptions that I can tell you is, for instance, we could start with predefined size distributions, right? And my predefined size distribution, sorry I don't have a figure here, but it could be, for instance, if I have a log normal distribution here, another log normal distribution here, another one here, and let's say I have 5 of those or 6 of those, and that could be one of the assumptions. I'm starting with 5 or 6 predefined log normal distributions. And then I asked my algorithm, how do I combine those predefined size distributions in order to get this fit? And you can see that I can get a very good fit. I have 4 parameters that I'm showing here. I could fit those 4 parameters very well. And the size distribution that was used to fit those, or the combination of size distributions that was used to fit those parameters very well, it gives you this overall final size distribution that you see here. So this has been intercompared and validated in many different ways. It's very hard to measure and intercompare size distributions, but in terms of optical inversion, I'm pretty confident that this is one of the best ways to do that inversion. And there are other algorithms, so many other researchers have similar algorithms to do inversions, and they achieve similar results. But one of the assumptions that I'm telling you is you start with some predefined size distribution, but it can be in a very loose way, like for instance, like 5 log normals. And then there are other assumptions, like a very strong one that really helps the algorithm is the continuity. Like we don't allow the algorithm for the retrieval to go crazy between this size beam and that size beam, for instance. So we put some constraint in terms of continuity, but just mathematical continuity in a very loose way, so that we don't have very crazy jumps. And I could go on and on, but that's the reason that we do the inversion, and that's just a very quick description of what you are trying to do with the inversion.
Okay, thanks, Vanderlei. We have maybe time for one more quick question. Yes, please.
Hi, Baron Henderson from the EPA. Thanks a lot for your talk. And I'm curious, right now you're relying on the motion of the polar orbiting satellite to get multiple angles. I'm curious if you had a constellation of many geostationary satellites, could you get simultaneous multiple angles, and what would the limitations on that be?
Yes, so obviously from a geostationary satellite, one geostationary satellite, you cannot get the multi-angle simultaneously. You could get throughout the day, right, as the sun is varying with a single satellite, but a better option is what you just described, right? So it's a constellation of geostationary satellites in different geometries looking at the same spot, and then at that spot you can get multi-angle simultaneously. The main, not limitation, but the main challenge, in my opinion, is now if you do that from a geostationary satellite, you need a bigger, I would say, a bit more complicated instrument to do that from space with the level of accuracy that we need. But it's just a technical challenge. We know how to solve it. And there are concepts like that. There are actually a couple publications where they propose measurements like that, right? So multiple satellites looking at the same point on the ground simultaneously and getting that measurement. So that's definitely possible, and I think it's a very nice direction.
Thank you.
Okay, and the benefit of time, let's thank Vanderlei one more time for...
Thank you very much.
Let's turn things over to Kelly with some award information.